Welcome to Chapter 5, Risk, Return, and the Historical Record. This is where the investments course starts putting numbers around two words that get used very casually: return and risk. Return is what we hope to earn. Risk is the range of outcomes we may have to live through before the final number arrives. That distinction matters because markets do not travel in straight lines. In 2020, investors experienced an extremely fast collapse and an equally remarkable recovery. In 2022, inflation and higher interest rates reminded everyone that stocks and bonds can both have a bad year at the same time. The historical record is valuable because it gives us evidence. It is dangerous when we treat that evidence as a promise. Throughout this chapter, keep one question in mind: which number answers the decision we are actually trying to make? A holding period return describes one investment result. A geometric average describes compound growth. A dollar-weighted return describes the investor's actual experience when cash moves in and out. A real return tells us what happened to purchasing power. Standard deviation and value at risk describe parts of the risk distribution, but not every possible surprise. The goal is not to collect formulas like baseball cards. It is to understand what each measure can tell us, what it cannot tell us, and how easily a technically correct number can answer the wrong question. Markets have never signed a contract promising to repeat their average. They do, however, keep very detailed receipts. This chapter has 4 practical learning objectives. First, you should be able to calculate a holding period return and separate the sources of that return. Did the investor earn income, price appreciation, or both? That sounds basic, but performance discussions often become vague the moment a dividend contribution or withdrawal appears. Second, you should be able to distinguish arithmetic, geometric, and dollar-weighted averages. These are not 3 competing versions of the same answer. They answer different questions. Arithmetic average is useful for thinking about a typical single period. Geometric average measures the constant compound rate that connects beginning wealth to ending wealth. Dollar-weighted return reflects the timing and size of the investor's cash flows. Third, you should be able to convert nominal return into real return and explain why inflation matters. A portfolio can show a positive gain in dollars, while purchasing power barely improves or even declines. A 10% return is not the same economic result when inflation is 2% versus 8%. Fourth, you should be able to interpret risk measures and historical risk premiums without pretending they provide certainty. Standard deviation, value at risk, skew, kurtosis, and the Sharpe ratio are useful tools. None is a crystal ball. Value at risk, in particular, sounds precise enough to wear a lab coat, but it remains a model built on assumptions. The assessment focus is application and judgment. A strong answer will calculate correctly, identify the appropriate measure, explain the assumptions, and state what uncertainty remains. The chapter is organized around 4 connected questions. The first question is return measurement. We begin with holding period return, then separate dividend yield from capital gain yield. From there, we decide whether an arithmetic average, geometric average, or dollar-weighted return best fits the task. The right formula depends on whether we are forecasting one period describing long-run compound growth or evaluating an investor's actual experience. The second question is inflation adjustment. Nominal returns are the numbers printed on statements. Real returns describe the change in purchasing power. The Fisher relationship connects nominal interest rates, real rates, and expected inflation. The arithmetic may be straightforward, but the economic meaning is the reason we care. The third question is risk measurement. We use scenarios and probability distributions to describe possible outcomes. Variance and standard deviation measure dispersion. Value at risk focuses on a downside threshold. Skew and kurtosis help us recognize that real-world returns may be asymmetric and may produce more extreme outcomes than a normal distribution suggests. The fourth question is historical evidence. We study the long-run returns and risk premiums of asset classes because history gives us a starting point for expectations. But the sample period matters, the economic regime matters, and the future is allowed to be rude. Think of the chapter as a sequence. Measure what happened, adjust for inflation, describe the risk around the result, then decide how much confidence the historical record deserves. That is a usable decision process, not simply a vocabulary list. This slide collects 6 concepts that students should be able to use in a sentence, a calculation, and an investment decision. Holding period return, or HPR, is the total return earned over a specific period. It includes both income and the change in price. It tells us what happened during that holding period, not what should happen next. The geometric average is the constant compound rate that reproduces the actual beginning and ending wealth. It respects the path of returns, which is why volatility lowers geometric growth. A dollar-weighted return is the internal rate of return on the investor's cash flows. It gives more weight to periods when more money was invested. That makes it especially relevant when an investor adds money near a peak or withdraws money near a low. Real return adjusts nominal return for inflation. It answers the question that ultimately matters for consumption. Did purchasing power rise? A risk premium is the expected return above a risk-free alternative. The word expected is doing important work. A premium is compensation investors demand for bearing risk, not a guaranteed bonus deposited at year-end. The Sharpe ratio compares excess return with total volatility. It is useful for comparing risk-adjusted performance when the assumptions and periods are comparable. A high Sharpe ratio is evidence, not a halo. The common thread is fit. HPR, geometric return, dollar-weighted return, real return, risk premium, and Sharpe ratio can all be calculated correctly and still be used badly. Finance has no shortage of precise answers to poorly framed questions. A disciplined return analysis can be organized into 6 steps. Step 1 is to identify the cash flows. Record the beginning value, ending value, dividends or interest, contributions, withdrawals, and any fees that are relevant to the question. This is where many mistakes begin. A performance dashboard may be accurate, but it cannot read the analyst's mind about which cash flows should be included. Step 2 is to calculate the holding period return for each period. Keep the units consistent. A monthly return and an annual return should not be compared without adjustment. Step 3 is to choose the correct average. Use arithmetic average when estimating an expected one-period return under appropriate assumptions. Use geometric average when describing multi-period compound growth. Use dollar-weighted return when the timing of investor cash flows is part of the story. Step 4 is to adjust for inflation when purchasing power matters. For long-term goals such as retirement or college funding, nominal wealth is not enough. The investor spends real dollars in the future, not a congratulatory percentage on a statement. Step 5 is to measure risk. Standard deviation may be useful, but examine downside scenarios, drawdowns, skew, fat tails, and the possibility that the historical sample is too calm. Step 6 is interpretation. Compare the result with the risk-free rate, an appropriate benchmark, the investor's objective, and the risk taken. A useful example is an investor who adds a large amount immediately before a market decline. The fund's time-weighted return may be unchanged, while the investor's dollar-weighted return deteriorates. Neither number is lying. They are answering different questions. Process discipline helps us ask the right one. The holding period return formula is simple. Ending price minus beginning price plus income divided by the beginning price. Suppose an investor buys a security for $100, receives $2 of income, and sells it for $108. The capital gain is $8. The income is $2. Total profit is $10 on a $100 beginning investment, so the holding period return is 10%. We can also decompose the result. The income yield is 2%. The capital gain yield is 8%. Together, they equal the 10% total return. That decomposition matters because income and price change may have different economic drivers, tax consequences, and persistence. The formula is easy enough to fit on a bumper sticker. Real portfolios are less cooperative. Contributions, withdrawals, reinvested distributions, multiple purchase dates, fees, foreign currency, and taxes can complicate the cash flow pattern. The correct response is not to abandon the formula. It is to define the measurement period and cash flows clearly. Also remember that a positive nominal HPR does not guarantee a positive real return. If the investment earns 10% while inflation is 8%, purchasing power increased by much less than 10%. The exact real return relationship divides 1 plus the nominal return by 1 plus inflation, then subtracts 1. Before using any return formula, say what the numerator represents, what the denominator represents, and whose experience is being measured. A formula without those definitions is just algebra wearing a tie. Arithmetic and geometric averages answer different questions, and volatility creates the difference between them. The arithmetic average is the simple average of periodic returns, but it is often used as an estimate of a typical one-period return. The geometric average is the constant compound rate that produces the same cumulative result as the actual sequence. Consider a 2-year investment that gains 50% in year 1 and loses 50% in year 2. The arithmetic average is 0%, positive 50 plus negative 50, divided by 2. But the investor did not break even. $100 grows to $150, then a 50% loss reduces it to $75. The cumulative loss is 25%. The geometric average is the square root of 0.75 minus 1, or approximately negative 13.4% per year. That number correctly links the starting value of $100 to the ending value of $75. This is sometimes called volatility drag, although the word drag can make it sound like a separate fee. It is simply the mathematics of compounding. A loss and an equal percentage gain do not cancel because they apply to different account values. After a 50% loss, the portfolio needs a 100% gain to recover. The arithmetic average says the average annual observation was 0. The account balance says otherwise. The account balance is a harsh but fair grader. Use arithmetic return for an appropriate one-period expectation. Use geometric return to describe compound history, and use dollar-weighted return when investor cash flow timing is part of the question. Modern portfolio dashboards calculate returns instantly, but instant calculation can hide the question being answered. What changed? Investors now see daily balances, performance charts, benchmark comparisons, and risk statistics on a phone. Fractional shares and automatic contributions make investing easier. Software can calculate time-weighted return, internal rate of return, volatility, and value at risk before anyone has finished their coffee. What stayed the same? Compounding, inflation, cash flow timing, and human behavior. An app can display a perfect geometric return while the investor earns less because money arrived after strong performance and left during a drawdown. Who benefits? Investors receive better access and more information. Advisors and platforms can monitor accounts more efficiently, but more frequent information can also encourage more frequent reactions. A daily performance chart is useful data, and for some people, a small anxiety machine. What risk remains? The biggest risk is assuming that the dashboard's number is the only relevant number. During the strong technology run of 2020 and 2021. Many investors increased exposure after prices had already risen dramatically. The 2022 reversal then created a painful lesson in dollar-weighted return. The fund's published return and the investor's actual experience could differ because the cash flows arrived at different times. Risk dashboards also depend on models. Standard deviation and value at risk may look scientific, but they are estimated from a sample and may understate regime changes, skew, and fat tails. The dashboard is not necessarily wrong. It may simply be answering a different question than the investor thinks it is answering. Always ask what changed, what stayed the same, who benefits, and what risk remains. Let's work through the practice case. An investor buys a stock for $40, receives $1.20 in dividends, and sells the stock for $45. Inflation during the year is 4%. Start with the holding period return. The capital gain is 45 minus 40, or $5. Add the $1.20 of dividends, and total profit is $6.20. Divide by the $40 beginning price. The holding period return is 15.5%. Now separate the components. Dividend yield is $1.20 divided by $40, which equals 3%. Capital gain yield is $5 divided by $40, which equals 12.5%. Together they equal the 15.5% HPR. For the real return, the quick approximation subtracts inflation. 15.5% minus 4% equals 11.5%. The exact calculation is 1.155 divided by 1.04 minus 1. That is approximately 11.1%. The final task is interpretation. Was the 15.5% return compensation for risk or simply a realized outcome? We cannot determine that from one observation. A risk premium is an expected reward for bearing risk across possible outcomes. This investor realized a strong result, but 1 year does not separate skill, luck, market beta, or an unusually favorable surprise. 1 good year is a data point, not a personality test for the stock. A strong answer gives the calculation, identifies the measure, and explains what the result does not prove. These 5 mistakes are common because each begins with a measure that is useful in the right setting. Mistake 1 is using an arithmetic average to describe multi-year wealth growth. The arithmetic average can be positive even when compound wealth falls. When the question is what happened to a dollar over time, geometric return is usually the relevant measure. Mistake 2 is ignoring cash flow timing. A fund can report a respectable time-weighted return, while an investor earns much less by buying after a rally and selling after a decline. Performance chasing turns timing into a hidden cost. Mistake 3 is treating standard deviation as the only form of risk. Volatility does not directly measure permanent impairment, liquidity failure, inflation risk, sequence risk, or the risk that an investor abandons the plan at the wrong moment. Mistake 4 is assuming a normal distribution when returns have skew and fat tails. The normal distribution is a useful map. It is not a restraining order on the market. The crises of 2008 and 2020 reminded investors that extreme outcomes can arrive more often and move faster than a calm sample suggests. Mistake 5 is using historical risk premiums as guarantees. Historical averages depend on the starting date, ending date, asset definition, inflation regime, valuation, and survival of the market being studied. History is evidence, not a coupon schedule. One related warning involves value at risk. VAR estimates a loss threshold at a specified probability over a specified horizon. It is not the maximum possible loss. The losses beyond the threshold are often the ones that make the meeting memorable. The cure for these errors is simple, but not easy. State the question, the measure, the assumptions, and the risk that remains. Here's the knowledge check. Which return measure gives the constant annual compound rate that matches actual cumulative performance. The correct answer is A, the geometric average. The geometric average is built from the full sequence of returns and produces the same ending wealth as that sequence. It is therefore the appropriate measure when we want to describe compound growth across multiple periods. The arithmetic average, choice B, is the simple average of the periodic observations. It can be useful for estimating a one-period expected return, but it does not necessarily reproduce the investor's beginning and ending wealth. Bank discount yield, choice C, is a quoting convention used for instruments such as treasury bills. Current yield, choice D, is annual income divided by the security's current price. Neither is designed to measure compound multi-period performance. A quick test is to ask whether volatility would make the arithmetic and geometric averages differ. When returns vary, the geometric average will generally be lower than the arithmetic average. The difference grows as volatility grows. So, the answer is geometric average. It connects the actual path to the actual ending value. In finance, the path matters, especially when the path includes a large loss, and someone is calmly insisting that the average was fine. Let's close with 3 takeaways. First, measurement choices change the return story. Holding period return, arithmetic average, geometric average, and dollar-weighted return are all legitimate measures. They are not interchangeable. The right measure depends on whether we are describing one period compound wealth or the investor's actual cash flow experience. Second, inflation can materially change the economic result. Nominal return is visible. Real return determines purchasing power. For long-term financial planning, ignoring inflation is like measuring a road trip in miles while refusing to discuss fuel. Third, risk premiums are uncertain compensation for bearing risk. Historical records help us estimate them, but the estimates contain sampling error and regime dependence. Standard deviation, value at risk, skew, kurtosis, and the Sharpe ratio help organize evidence. None eliminates uncertainty. After the slides, the homework asks students to measure and interpret returns. The discussion asks which return number investors should care about. The quiz checks the core concepts and calculations. The next chapter moves into efficient diversification. That progression is deliberate. We first need reliable estimates of return, risk, covariance, and risk premiums. Then we can ask how assets should be combined. Bad inputs do not become good just because the portfolio optimization has more decimals. Finish with one question: what fact would change my recommendation? That question forces us to separate a calculation from a decision. A good analyst knows the answer. A great analyst also knows what could make the answer wrong